My name is Kevin Jones. I will be presenting IoT Formal Security Analysis of Smart Embedded Systems, a paper by Farid Mulazim Tabrizi and Karthik Pattabhiraman. Apologies if I mispronounce those names. You can correct me on Piazza. This paper specifically deals with security in embedded devices, or the Internet of Things. The paper describes the Internet of Things as a collection of network-enabled physical objects that are embedded with sensors and software and to collect and exchange data. These embedded devices are more and more becoming a target for hackers as they are increasingly becoming integrated into safety-critical systems, and because they're low performance, they're often relatively easy to break into. So examples, as we're seeing in this class, things like electrical infrastructure. They're also in things like cars, cell phones, smart home devices. There are a range of applications in which these embedded devices are popping up. So this paper specifically looks at formal analysis as a way of analyzing the security properties of these embedded devices. So formal analysis uses mathematical techniques to analyze system behavior. It provides full coverage of possible system behavior, unlike simulation or testing that can only cover specific behaviors and a specific set of inputs. The coverage of formal analysis is dependent on the quality of the model used and on the type of analysis. Some analyses are time-bound, others are more abstract and will cover the full state space. As I'll talk more about later, some of the different models are based on a system specification, whereas others are derived from the actual implementation of the embedded device. For this paper, they use a type of formal analysis called model checking, which uses a series of temporal logic formulas to express system behavior, and then compares this system behavior against system specifications. In this case, different security properties and different behaviors that may be, or access to data rather, that may be problematic for the security of the system. Now, using formal analysis for security properties does come with its own challenges. It requires, first of all, a formal specification for the system. Prior to this paper, there had been some formal analysis used for other embedded devices, but because they were limited to those embedded devices, it did not allow for analysis of things like the smart power meter that is analyzed in this paper. The analysis is only as good as the model, so for each embedded device you have to create a high-quality model that will capture the behavior of the system. And then, as I mentioned before, this may be based on the specification of the system, as is done in this paper, or may be based on the actual implementation of the system, using actual hardware description language code, or measured values from the system as a possible range of inputs to your model. Another challenge is the state space explosion problem, which is simply that the state space, or the set of possible behaviors of the system, grows exponentially with system complexity or the size of the model. So as a model grows larger, the state space that needs to be analyzed grows exponentially larger and can very quickly get out of hand for a large system. The language used for the specification in this paper is rewriting logic, which is their formal syntax for writing the proof systems for their model checking. It is a four-tuple of sigma, e, l, and r, where sigma is the set of all functions and constants, e is the set of all equations for the model, r is the set of labeled rewriting rules, and l is the set of those labels. These rewriting rules model transitions in the system. So if you think of it as something like a state machine, then the rewriting rules are what model the movement between those states when the system changes. And then the labels on those rewriting rules describe how the system changes, how different variables change, and things of that sort. So this was implemented using the mod language for the experiments used in this paper. So if we look at the behavior of the smart meter, the model that is being used, it consists of three primary units. The control unit, which essentially runs the system and decides how the operations are performed. There is the communication system, which allows the smart meter to communicate with a network, with the electrical infrastructure in this case. And then there is the clock that keeps everything synchronized and is used for time of use billing for peak time. So you can see in the diagram the model of the data flow in the system, which is what specifically is modeled in this paper. To model the whole smart meter would be would be too large for the scope of a single paper. And so they focus on the data memory. My presentation will be even a little bit more focused than that, as you'll see in the following slides. And I would refer you to the paper for additional information on the data flow and how it was analyzed. So from here on out, the paper gets a little bit math heavy. I'm going to try to give a general intuition at a high level. I would refer you to the paper for the full mathematical details. And if you have any questions on Piazza, I would be happy to address them. If any of this is unclear, we can go a little bit more into depth in a future discussion. So to start off with, to show the formal model for just a part of the smart meter behavior. Again, this is focusing on the data flow, and this specifically only includes how the data is collected. So on the left, you can see a diagram. You have an array of sensors that are feeding into the microcontroller, which on the right are represented as a list of tuples, where each one consists of the sensor and the value that sensor has. And then that array, or the values in that array, will change over time. So on the right, you have the description of that in the mod language. So line 2 defines the different data types. You have the sensor element, sensor list, sensor number, and sensor value. So on line 3, you can see the sensor element defined as two natural numbers, one which corresponds to the sensor, the other which corresponds to the value. In line 4, you have the sensor list, which is defined as a stream of sensor elements, or that array in the diagram on the left. On line 5, we have the function has sensor defined, which is the base case of the recursive function in line 8, has sensor, which in essence just says whether a sensor has valid data on it. And then the data list is the actual variable that holds the data for that sensor list. So this is just defining, again, the behavior of the sensors collecting the data and then storing them in the microcontroller. The paper also includes similar functions for how the data is passed within the microcontroller and then onto the network. For the sake of brevity, I have not included them in this presentation. So moving on to the threat model, we assume for this threat model that the attacker is able to drop and replay messages both to and from the microcontroller, and that the attacker is able to restart the meter. The attacker is not assumed to be able to decrypt encrypted messages or to spoof cryptographic tokens. So we assume that if cryptography is with the assumption that cryptography is being used, that the cryptography is properly implemented and the attacker does not have access to what is inside of the encrypted messages. So you can see in this table a brief overview of the capabilities the attacker is assumed to have. They may have physical access to the device, they may have physical access to the communication interfaces, Ethernet or Wi-Fi, and they may have access to a routing node in the grid network infrastructure. So if the smart meter is connected to the internet, they may have control of an internet router in some form. Now, it may be noted that none of the capabilities that they are assumed to have actually require physical access to the device. It may be possible for them to reboot the machine simply by cutting power to the area or something to that effect. And then the network interfaces can be accessed remotely. They do not actually require physical access to the device. So to show the formal specification of the attacker's threat model, of the attacker's capabilities, essentially here we have the variables of the different system elements that the attacker may either gain access to or modify. We have the sensor data elements, we have the state of the system, and the node number there. But then at the bottom, lines 8, 9, and 10 are the most interesting parts. So these are the actions that the attacker may perform. He may drop a message from the network, so essentially a message from the server to the device or vice versa. He may reboot the server. He may reboot the device, or the attacker may replay a message that has been sent over the network, either from the server to the device or vice versa, from the device to the server. So those are the three main capabilities that the attacker is assumed to have, and we want to see whether the device is vulnerable to any of these three attacks. The testbed that was used for this was used the SegMeter open source smart meter software that was running on an Arduino board, as shown in the figure. The Arduino board was connected to a gateway board for networking. It did not have its own network interfaces, and that gateway board included LAN and Wi-Fi interfaces. So those were the physical media over which the device was connected to the network. So the paper presents analyses of each of those three capabilities, the three attacks that the attacker was assumed to be able to use. First was the reboot attack. So in this case, on the bottom you have just a small, essentially state diagram of the machine's behavior. The solid lines and circles are the built-in expected behavior of the device, and the dotted lines are the extra transitions that are included when the attacker performs a reboot attack. In this, the model found a vulnerability when the reboot occurred during data transfer. The data transfer was not being properly acknowledged, and data was being lost during a transfer. Essentially the transfer was interrupted. The device had deleted the data because it was in transit, and the server had not yet received the data. So this data was lost on 14 out of 20 tries when they actually performed this attack on the test bed. Occasionally, the entire data file was erased from the system, not just the data that was in transit. There was an implementation bug where a file was opened in write mode instead of append mode, and because with the intention that the data would be written back into the file during the write phase. So because the system was rebooted during that write phase, that never actually happened. So on 3 out of the 20 tries, the entire data file that was being modified was deleted. So in this case, even though the formal model did not fully describe the implementation, it did lead to the discovery of implementation bugs that were similar to higher level sort of specification errors within the description of the system. The next attack that was evaluated was the message dropping attack. So this interfered with the time of use billing. The time of use billing on the smart meter required proper time synchronization with the server. Kind of makes sense. If you want to charge based on usage for different times of day, then you need to know what time of day it actually is. So in this case, the state diagram at the bottom shows the expected behavior of the system in solid lines and circles, and then the added behavior of the attacker is shown by the dotted line in state 6 there. So typically the device would check in with the server to get the updated time, and then receive the response with the updated time and update accordingly, and then it would have a flag to keep track of whether the time was valid. It would have some set interval in which it was expected to check back and get the correct time. So if the attacker was able to drop messages, then it could prevent the device from getting those updated times from the server. So in practice, this led to the smart meter hanging. Essentially, the smart meter would say, my time isn't valid. It would ask the server for an updated time. It would never get a response back. And so the device would just say, well, okay, I don't have the correct time, so I'm not going to do anything because I cannot guarantee proper time of use billing because I don't know what time it is. And so this essentially would be a denial of service attack for the device, that the device would stop recording data. The final attack that was analyzed was the replay attack. So in this case, again, we're assuming the attacker has some access to the network, is able to collect messages that are being sent, in this case, from the server to the smart meter, and that it can then replay those attacks at a later time. So the formal model found that replaying a message could coax the meter to send data when no connection was open. Essentially, the meter would think that the server was listening when the server was not actually listening. So it would send data to the server to be collected, but the server would not have a port open to receive that data. So this resulted in lost data. And this attack was successfully mounted against the seg meter by the attacker sending a message to the device telling him that the server was listening. The device was prompted to send data to a closed port on the server, which data was then dropped, deleted from the device, and lost. We can see from these examples that the complete coverage that formal methods offer offers can be very useful to find security flaws. Often these security weaknesses are hidden in corner cases and obscure sections of the system behavior that a system designer may not necessarily think to check. However, there is always a trade-off between performance and accuracy when performing formal verification. This method was based on specification, as I mentioned before, not implementation. And so while in this case it was able to find a bug in the implementation of the smart meter design, it is not guaranteed that it would find every weakness in the implementation. And in fact, it cannot find any actual implementation bugs. It can only lead a designer to inspect areas of the design where the implementation may be weak. So methods that are based off of implementation would provide that extra coverage of finding weaknesses in the implementation that are not problems with the specification itself. However, this gives the trade-off that they are larger models, therefore more difficult to analyze, and you run into that state space problem that I mentioned before. So I've worked on a couple of different projects at different institutions that have worked to deal with this problem. One of them was using formal verification methods, analyzing hardware description language models that used bounded model checking. So this was time-bounded, and so it did not cover the entire state space. It basically covered all behavior of the system within the first n clock cycles. And then another project that I worked on used a mathematical model that used conservative abstractions. So rather than including all the detail of the implementation of the model, it would create convex polygons that would include all of the state all of the behavior that the model could actually do, in addition to additional behaviors that were not actually possible. So this introduced some potential false negatives that would essentially give an engineer or scientist additional work to analyze whether potential threats were real threats or simply false negatives. I haven't cited that work in this presentation, but if you're interested, let me know and I can point you to those papers. They're rather old, haven't been very widely published, but they are available if you're interested. So that is my brief analysis of using formal verification to verify security properties of embedded devices. If you have any questions, feel free to post them on Piazza and I'll be happy to answer them. Thank you.